Alright, so today we're going to talk real quickly about the notes and concepts from section 2.1 to 2.3, and what we're really focusing on are our sine and our cosine values, and how we can expand those past triangles that you're used to. So we start by having to talk about our definition of angles. So we're going to define standard position. And standard position is if we start with our y-axis and our x-axis, and the vertex of our angle is given at the origin. The initial side of our angle, our ray, is along the positive x-axis. If our terminal side happened to be in quadrant 2, our angle would look like this, and we define the angle as theta, the Greek letter theta. So we also want to note that this direction is going to be our positive direction, so counterclockwise. If we were to go clockwise, that would be a negative angle. And in general, so our angle can be anything that we want. It could be between 0 and 360 degrees, it could be 720 degrees, it could be anywhere in between. We can rotate as many times as we want. But because we're going to talk about triangles, we also define what is our reference angle. Shown here as theta sub r for the reference angle. And that's always an acute angle, and it's always formed between our terminal side and the x-axis to give us an acute angle to deal with. So there's a question. The question is, given some point, x comma y, will it form a unique angle? And if you start thinking about it and plot a point, there's x, y, there's an angle theta. We can notice pretty quickly that if I add 360 degrees, I have the same terminal side, 720 degrees, the same terminal side. And so there's going to be infinitely many angles that go through this point, x, y. And if this happens, if we have angles that have the same terminal side, they are said to be coterminal. So geometrically, this is what it looks like. If we were to look at it mathematically, if I have angles theta and phi, they're said to be coterminal if phi is theta plus n times 360 degrees, where n is an integer. And so again, all this is really doing is it's saying if I have my axes and I have an angle, so this would be theta, if I take that value and I add a multiple of 360, it's going to be the same terminal side, and then phi in this case would equal theta plus 360 degrees. And in this case, n, the integer, would be 1. So that's all it's saying mathematically. So we have the geometric interpretation, rotations of 360 degrees, and we have the mathematical one with this equation up here. Alright, so the big question is, how does this relate to trig? Alright, so let's just remind ourselves real quick about what trig, as we've seen it before, is. Trig can be ratios. So if I take a right triangle, I have angle A, I label my sides adjacent, opposite, and hypotenuse. And sine of A is opposite over hypotenuse. Remember, the hypotenuse is always across from the 90-degree angle. My cosine of A is adjacent over hypotenuse, and we're not going to talk a lot about today, but we also have tangent of A, which is opposite over adjacent. And if you have trouble remembering that, you can remember the acronym SOHCAHTOA. That is a mnemonic, a way to remember sine, cosine, and tangent, if you ever get it confused. Okay, so let's think about our trig ratios as trig functions as ratios. And the question is, what is the domain for sine A, cosine A, and tangent A, where A is an angle in a right triangle? So we're restricted to a right triangle. Well, let's think for a second about what domain is. Domain is, if we have a function, it's the values that we put into a function. The range is what we get out of a function. So the question is, if I have a right triangle, A is going to have to be less than 90 degrees. If it's not, if I try to fit two 90-degree angles in a triangle, I don't get a triangle, right? These two sides are never going to meet to give me my triangle. So A has to be less than 90 degrees. So our domain is going to be less than 90 degrees. The range, if we think about it, is also going to be restricted. I have this side here. Let's just call it, let's look at sine, for example, and let's say this is x and this is y, right? Well, sine would be x over y. But we can use the properties of a triangle, of our geometric properties, to know that the hypotenuse is always going to be the largest side. So this value, sine, is going to have to be less than 1. And as we expand our domain, we're going to sort out that we can change this a little bit. We can get a little more leeway on it. So can we extend the domain? Well, let's see. Let's say I take a point, 3, 4, and we pick this for a purpose. It's in quadrant 1. I draw my right triangle. Here's my point, 3, 4, and then using the Pythagorean theorem, we're recognizing that it's a Pythagorean triple. Here is my sides. I define the angle theta. Sine of theta is opposite over hypotenuse, is 4/5. Cosine of theta is 3/5. Tangent theta is going to be 4/3. This is our current domain. Okay, theta could be anything in there. But let's try to expand a little bit. Let's look what happens if we were to go to quadrant 2, quadrant 3, quadrant 4, and take my triangle and use some reflections, and it'll show up like that. Well, what's different here is now I have some negative values, right? This is a -3 in this direction. This is still a +4. This is going to be a -4, and this is going to be a -4. The reason that we want to do this is that the triangle here in quadrant 1 is a different point, a different ray, a different angle, deals with this angle, as opposed to this angle over here. Alright? So we want to have some notation around that. So if we look at our values, we define sine is 4/5, cosine is -3/5. Alright? Sine of theta here is -4/5, cosine is -3/5. Sine here is -4/5, cosine is 3/5. Well, let's take a look at how the ordered pairs relate to our values, our trig values. So we see that the x-coordinate went to cosine in the first quadrant, the y-coordinate went to sine. Same thing in the second quadrant, same thing in the third. Same thing in the fourth. Alright? So we get this generalized expanded definition for our trigonometric ratios. Alright? And it's a coordinate definition. So if we take a coordinate, a point u comma v, and we define the distance r, alright, and we could find that with the Pythagorean theorem if we wanted to. There's our angle theta. Cosine is defined as u over r. Sine is defined as v over r. And if the triangle definition is easier for you to think about, if you look at this, remember we would really still, since we're on the coordinate grid, we'd have a right triangle, and I would have a distance here of u, a distance here of v, and my trig ratios are still going to be the same. But what this allows me to do is expand, alright, to a point that would be in the second quadrant, or the third quadrant, or the fourth quadrant. And if this is point back here, -1, 2, 3, 4, 5, -5, -1, well, in my definition over there, this is going to be u, this is going to be v. What I'm missing, the piece that I need to find, is going to be r. And r is just going to be part of a right triangle, and we use the Pythagorean theorem to find it. Alright. The big difference, again, is theta can be any angle. It's not restricted to that first quadrant between 0 and 90 degrees. Alright, so your turn. You're going to look at these examples on this page, try to solve them using our expanded definition.